To achieve the desired gate light control, employing an electromechanical relay with normally open contacts, a capacitor, and a resistor is required. When the push button is activated, the 110-volt supply circuit is completed, which in turn applies power to the relay coil. The relay coil energizes, and the normally open contacts close as a result. The gate lights turn on as power flows through the now closed normally open contacts. At the same moment, the capacitor begins charging through the resistor. As the capacitor charges, a voltage develops across its terminals that opposes the flow of current through the relay coil. After a duration of approximately 15 minutes, or whatever time delay is desired, the capacitor voltage builds up sufficiently to diminish the current through the relay coil, reaching a point where it is no longer capable of sustaining the normally open contacts in a closed position. Consequently, the normally open contacts open and the gate lights switch off. The time delay in seconds is determined by the formula T equals R times C, where R represents the resistance in ohms and C represents the capacitance in farads. For a 15-minute time delay, the following values can be used: R equals 100,000 ohms and C equals 0.22 microfarads. It is important to select a capacitor with a voltage rating that surpasses the supply voltage. The relay coil must be appropriately rated for the supply voltage and current requirements. The resistor should be a high resistance value to minimize current consumption. To elaborate on the function of each component, we begin with the electromechanical relay. An electromechanical relay is essentially an electrically operated switch. It utilizes an electromagnetic coil to mechanically actuate a set of contacts. These contacts can either be normally open, meaning they are open in the de-energized state and closed when the coil is energized, or normally closed, meaning they are closed in the de-energized state and open when the coil is energized. In this specific application, a relay with normally open contacts is essential to control the gate lights. Secondly, the capacitor stores electrical energy in an electric field. It consists of two conductive plates separated by a dielectric material. When a voltage is applied across the capacitor, it accumulates electric charge on its plates. The amount of charge a capacitor can store for a given voltage is its capacitance, measured in farads. In this circuit, the capacitor plays a crucial role in creating the time delay, acting as an energy reservoir that gradually charges and influences the relay coil current. The resistor restricts the flow of electric current. It is a passive component that dissipates electrical energy as heat. The resistance of a resistor, measured in ohms, determines the amount of current that flows through it for a given voltage. In this circuit, the resistor, in conjunction with the capacitor, governs the charging rate of the capacitor, thus controlling the time delay. To delve further into the operation of the circuit, when the push button is pressed, it provides a momentary closure of the 110-volt supply circuit. This action energizes the relay coil. Upon energization, the relay coil generates a magnetic field which attracts a movable armature within the relay. The armature is mechanically linked to the normally open contact. The magnetic force pulls the armature, causing the normally open contacts to close. With the normally open contacts now closed, the gate lights receive power and illuminate. Simultaneously, the 110-volt supply also begins charging the capacitor through the resistor. The resistor limits the current flowing into the capacitor, causing the capacitor to charge gradually. As the capacitor charges, the voltage across its terminals increases exponentially. This voltage opposes the flow of current through the relay coil. The higher the voltage across the capacitor, the less current flows through the relay coil. This is because the capacitor acts as a voltage source opposing the applied voltage. The time it takes for the capacitor to charge to a certain voltage is determined by the time constant of the circuit, which is the product of the resistance and capacitance, as expressed in the formula T equals R times C. This time constant dictates the delay before the relay coil de-energizes and the gate lights turn off. After the predetermined time delay, the capacitor voltage reaches a level sufficient to significantly reduce the current flowing through the relay coil. The magnetic field generated by the coil weakens to a point where it can no longer hold the armature in a closed position. The spring force of the relay mechanism overcomes the magnetic force, causing the armature to return to its original position. As the armature moves, the normally open contacts open, interrupting the power supply to the gate lights. As a result, the gate lights turn off. The accuracy of the time delay depends on the tolerance of the capacitor and resistor values. Real-world components have variations in their specified values. For example, a capacitor labeled as 0.22 microfarads may actually have a capacitance slightly above or below that value. Similarly, a resistor labeled as 100,000 ohms may have a resistance that deviates slightly from that value. These variations can affect the charging rate of the capacitor and therefore the time delay. To minimize the impact of component tolerances, use high-quality components with low tolerance ratings. For example, use resistors with a 1% tolerance or capacitors with a 5% tolerance. Alternatively, a potentiometer can be added in series with the resistor to allow for fine-tuning of the time delay. A potentiometer is a variable resistor that allows you to adjust the resistance value manually. By adjusting the potentiometer, you can compensate for variations in the capacitor and resistor values. Further considerations include the selection of the correct capacitor voltage rating. The capacitor must be able to withstand the supply voltage without failing. Choose a capacitor with a voltage rating that is significantly higher than the supply voltage to provide a safety margin. For example, if the supply voltage is 110 volts, use a capacitor with a voltage rating of 200 volts or higher. The relay coil must be rated for the supply voltage and current requirements. Ensure that the relay coil voltage matches the supply voltage. The relay contacts must also be able to handle the current drawn by the gate lights. Check the relay specifications to ensure that the contacts are rated for the appropriate current. The resistor should be a high resistance value to minimize current consumption. The higher the resistance value, the less current will flow through the resistor. This reduces the overall power consumption of the circuit. However, the resistance value should not be too high, as this can affect the charging rate of the capacitor. The choice of resistance value is a compromise between minimizing current consumption and achieving the desired time delay. Regarding safety considerations, always disconnect the power supply before working on any electrical circuit. Use appropriate safety precautions, such as wearing safety glasses and gloves. Ensure that all connections are secure and properly insulated. If you are not comfortable working with electrical circuits, consult a qualified electrician. If the time delay needs to be adjustable, the resistor can be substituted with a potentiometer. Using a potentiometer allows to increase or decrease the overall resistance in the circuit, which directly affects the charging time of the capacitor, and thereby allowing the user to change the length of time the lights stay on after the button has been depressed. Another advanced method involves using a 555 timer IC in monostable mode. This configuration provides more precise and stable time delays compared to a simple resistor capacitor circuit. The 555 timer IC is a versatile integrated circuit commonly used in timing applications. In monostable mode, the 555 timer IC produces a single output pulse of a predetermined duration when triggered. The duration of the pulse is determined by the values of an external resistor and capacitor connected to the IC. The output pulse can be used to control a relay, which in turn controls the gate lights. Firstly, the 555 timer IC provides greater accuracy and stability compared to a simple resistor capacitor circuit. The timing is less susceptible to variations in component values and temperature. Secondly, the 555 timer IC allows for a wider range of time delays. The time delay can be easily adjusted by changing the values of the external resistor and capacitor. Thirdly, the 555 timer IC provides a clean and well-defined output pulse, which ensures reliable operation of the relay. To implement the 555 timer IC circuit, connect the 110 volts supply to the 555 timer IC through a voltage divider to provide the appropriate voltage for the IC. Connect a push button to the trigger input of the 555 timer IC. When the push button is pressed, it triggers the 555 timer IC to generate an output pulse. Connect the output of the 555 timer IC to the relay coil. The output pulse energizes the relay coil, causing the normally open contacts to close and turn on the gate lights. The duration of the output pulse is determined by the values of the external resistor and capacitor connected to the 555 timer IC. After the pulse duration has elapsed, the output pulse terminates, de-energizing the relay coil and turning off the gate lights. The 555 timer IC circuit offers a more sophisticated and reliable solution for controlling the gate lights compared to the simple resistor-capacitor circuit. In summary, there are multiple ways to achieve the desired functionality. The choice of which method to use may vary depending on the level of control, budget, and required reliability.